Welcome back, everyone. I'm Mike Berman, and I'm going to talk to you about my program in molecular dynamics and theoretical chemistry. Oh, I guess I've got control here. Okay. The program that I manage really deals with fundamental issues in understanding and exploiting chemical reactivity and energy flow in molecules. So John Schmischer's last talk showed you some examples of the importance of energy flow, energy transfer, and reactivity. And I'll tell you about an increasing area of focus in our program, looking specifically at exploiting chemical reactivity and catalysis for improved storage and utilization of energy. And by improved storage and utilization of energy, I mean making fuels, using fuels, and then understanding the consequences of using those fuels. And I'll explain that a little bit as we go along. Okay, so we're... All right. Hi, I'm Mike Berman, and okay.
Maybe it's turned off. Sure. There we go.
Okay.
That was why.
All right. Okay. So in the program, we cover a wide range of areas, and I'll tell you a little bit about some of the challenges that we face. In energetic materials, where we try to create new propellants or explosives, the field is really faced by reaching or coming to a plateau of a limit of what you can get with energetic materials based on carbon, hydrogen, nitrogen, and oxygen. So we've been looking at new approaches to the traditional types of organic chemistry-based explosives or propellants. So we pioneered work in the area of energetic ionic liquids as energetic materials. I'll tell you a little bit about some of those. Some work on energetic nanostructures, specifically some metal clusters that are particularly stable and energetic. Mike Lindsay at Eglin Air Force Base is working on some novel materials that can be made in helium nanodroplets, so some unique environments to make some unique materials. Then in atmospheric and space chemistry, there are a lot of important areas where there's fast and important chemistry that goes on. John Schmischer just gave a nice discussion of the gas surface interactions that occur in hypersonic flight or high-speed flight in the upper atmosphere or in space. So we try to understand the dynamics of those chemical processes going on. Some cases measure rates that go into the models that John is talking about. There are often signatures when one burns fuels. So if we have new fuels like these energetic ionic liquids, what are going to be the signatures from those if they're used in aircraft or in satellites? So that really has an impact on space situational awareness. So folks in the RV Directorate are looking at some of the signatures and the rates of the reactions of energetic ionic liquids. And we're also looking at ion molecule reactions, processes that occur in plasmas, reactions that occur with electrons and ions, try to measure those rates, put them into predictive codes for communication blackout so we can understand those types of situations. Another area is dealing with nanostructures. And we're, as I mentioned, looking particularly at applications of nanostructures for catalysis. With nanostructures in these areas, we're really looking at chemistry that's different than in the bulk phase. So when you get small, different types of chemistry occurs. Often that's catalytic. And so those are some of the things that we're trying to look at, particularly for applications to energy and energy utilization, making fuels. We'd like to be able to understand the mechanisms of catalysis so we can control and optimize what's going on. Finally, lasers and diagnostics. One of the areas that we're working in is in high-power gas lasers. These are hybrid electrical chemical laser systems. Howie Schlossberg mentioned a little bit about this the other day, where many of these laser systems really are mode converters. You can take efficient energy from diode pump lasers. We can then use the gas system as a way to make high power beam but with good beam quality. And we're looking at interesting ways of doing that. I wanted to focus a little bit more on catalysis and tell you about some of the scientific challenges and opportunities in this area. What catalysis does is it lowers the activation energy for a process, so it makes processes that are often prohibitively slow into a practical process. So in doing so, it's really transformational. It takes something that usually doesn't occur and make it occur at a rate that's useful. One of the most important historical examples of catalysis being transformational is the Haber-Bosch process, where we could turn nitrogen into ammonia, which can then be used to make fuels, munitions, and fertilizer. That really transformed, it transformed societies, really, as well as the military, over 100 years ago. So we're looking for new transformational opportunities. And it turns out that catalysis is really key to energy storage and utilization. Many schemes and opportunities for new fuels really revolve around, are limited by the catalyst. We need to find new catalytic methods for doing that. And almost every fuel that we use touches a catalyst at some point in its processing. So a lot of military and important military and industrial applications of catalysis. Catalysts have been around for a long time, but there are really a lot of parts of the mechanisms of how catalysts work that we don't understand. People use promoters, co-catalysts, different types of substrates. We really don't understand the mechanisms, and that's the area of emphasis that we're looking at, because really in the last 10 years or so, we've developed new ways to manipulate nanostructures, to both prepare nanostructures, to probe nanostructures, and predict the properties of nanostructures. So being able to take these new developments and apply them to catalysis, we really think we'll be able to make new strides in understanding, controlling, and exploiting catalysis. Another area that we're also looking to exploit in chemical reactivity is plasmonics. You heard a number of talks already talking about plasmonics in electrical applications, making electronic devices. But what plasmonics are doing with particles that are often the same size and structure as are used for catalysis, they're concentrating electromagnetic fields, surface, plasmon, polaritons. You're creating high local electromagnetic fields. So we'd like to see if we can exploit that for chemistry as well. Can we use those fields to drive some novel chemical reactions? Okay, so transformational opportunities. One of the main and most important things that we're trying to do is create secure and sustainable energy supplies. Put simply, we'd like to transform CO2 into JP8. So that's an interesting and challenging task. Any fuel that we have, any hydrocarbon fuel, has many carbons strung together, bound together, lots of carbon-carbon bonds. So the goal here is to find a way to catalytically take CO2 to activate it and make carbon-carbon bonds out of it. And to do that, we'd like to also use some sustainable inputs. So we'd like to do this with solar energy or wind energy, some clean way to produce electricity. But electricity, you can't use electricity these days to directly power an aircraft. The problem with these sustainable sorts of energy is that they're not storable. You can't easily store them in quantities. So in order to fuel our aircraft, we really need some high-density liquid. So we're going to be flying our planes with some type of liquid fuel. When you burn a liquid fuel, you're going to make CO2 as the product. What we'd like to have then is a carbon-neutral system. If we're producing CO2 in the end, if we can make the fuel from CO2 in the beginning, we'd have a carbon-neutral cycle. And as well as if we can find a way to find reactions that use up CO2, we're also finding a way to sequester CO2 from the atmosphere. So that's one of the overall transformational type of goals that we're looking for. Another thing is using endothermic fuels to cool high-speed vehicles. So in high-speed, hypersonic type of vehicles, they're often limited by heating of the materials. And fuels are often used to cool them. By using catalysis, we can enhance the heat sink capability of those fuels. So those are no new emissions that would be enabled by catalysis. Here, the fuel flows through narrow channels in the heat exchangers. Having catalysts in there or catalysts in the fuel can help us enable new types of missions. Also transformational are using dual mode propellants for satellites. And these are ionic liquids that could be used both for the main thrusters as well as for station keeping. So that could enable new types of missions to be conceived. Other people working in these fields of catalysis and energetic alternate fuels, NSF is certainly covers all areas of chemistry. They have a special program, a center on powering the planet. Our goals are a little bit more modest. We just want to power the Air Force, but it's still a challenge. In DOE, Basic Energy Sciences, they have a new hub or a large center on solar fuels where they really want to take everything from research all the way through to industrial scale production. So they're looking to integrate a lot of this. It's a congressional line item for all the benefits and possible negative aspects that has. Who knows how long the funding for that might last. But part of the team that we have in a new MURI, also in this area, some of the team members are also as part of this hub on solar fuels, and they say the real basic understanding of mechanisms is going to be done through the AFOSR MURI program. So this is really the niche that we're looking for, understanding the fundamentals and the underpinning work on catalytic mechanisms. And really, in kind of with some missionary type zeal, I've been trying to twist arms or move people in the physical, chemistry, chemical dynamics community to use the methods they've had to look at these more complex systems, understanding these catalytic mechanisms. And you'll see some examples of that. We want to try to understand what are the active sites of catalysts. Can we make size-selected clusters that use catalysts, and can we control catalysis? So overall program trends, yeah, you can see catalysis, sustainable energy as areas that are increasing. Small molecule activation stems from a new ideas initiative that we've had ably put together by Ken Castor. It's going to fit in nicely with our program with activating small molecules, activating nitrogen, CO2, making them reactive so we can put them together to form energetic materials. These areas staying the same. Some of these areas that are decreasing in attention are not because of lack of interest, but in fact because of so much interest in other areas. Lots more people talking about modeling of materials and sensors, so that's kind of transitioning onto other programs. Some recent transitions from the program itself. I mentioned some novel types of energetic materials we looked at in our program, particularly with Kit Bowen at Johns Hopkins, Will Castleman at Penn State, in developing these energetic aluminum clusters that are both energetic and stable to oxidation. Funding, so we funded some of this initial work. It's been picked up now by folks at DITRA and ONR to try to turn this into a larger scale process, make more macroscopic materials. Jim Lightstone at Indian Head is developing some of this in the Navy 6.2 programs. Kit Bowen at Johns Hopkins spent some time working in Germany with a scientist named Schnuckel, who was able to make these aluminum-based clusters in a very interesting device, make them in macro scale with certain ligands. And he learned this technology and brought it back to the US and built these devices, which they call a Schnuckelator, to make these aluminum clusters in large quantities. He made one for himself, which he's now sharing with someone named Brian Eichhorn at the University of Maryland, and helped the Navy folks construct one. And here's an example, a picture of some of the first material that they've made. So you can make these not just in a laboratory scale in vacuum chambers that many of the people in my program are used to working, but real macroscopic quantities of some of these type of clusters. Another area that we've been able to transition is some applications of atomic layer deposition. We've been working in this area for quite a while. You see it pop up in other programs frequently these days, but Steve George at the University of Colorado has pioneered a lot of this work in this program. Now, so atomic layer deposition gives you the capability to put down conformal coatings and control them one atomic layer at a time. So you can really control the thickness, and they're also done very defect-free, so you can make very nice solid coatings. This application is being pursued by DuPont on flexible solar type of cells, where the coating is used to prevent oxygen and water penetration, so it's a gas barrier. And 10 nanometer, a coating that's 10 nanometers thick provides equal protection as a large piece of glass does. So you can make these flexible and very thin. Here's an example. You can see this is the ALD coating, which is very uniform. A CVD type of coating has lots of pinholes and gaps in it. So it's very nice as a protective barrier. Boeing is also looking at this type of technology to coat aircraft canopies against protection. We also had an STTR, actually 2 STTRs in this area to develop space coatings, where again, you can use a very thin coating in the space environment to protect against oxidation from oxygen atoms. And that's been quite successful.
For the solar voltaics,
Yes.
Do you have a metric on whether that improves efficiency by a significant amount?
Yes, I don't have the specific metric, but offhand, but the water and oxygen penetration was limiting the capabilities of these particular types of solar cells, these flexible solar cells. So it's really an enabling type of technology to put those into more widespread use. Okay, so with those transitions now, I'll tell you about hopefully what will be our transitions of the future. And this is some of the work that we're starting on trying to convert CO2 into fuels. This picture has been around a little bit already. This is the work of Andy Bacarsley at Princeton University, where they've tackled this challenge of converting CO2 into fuels. And it's a very difficult challenge. In electrochemistry terms, it's a 6-electron process. So you have to put in 6 electrons to go from CO2 to methanol. What we'd like to do is to go even beyond that into larger hydrocarbons, go all the way to things that can be used as fuels, larger alcohols, propanol, which has 3 carbons, butanol, larger types of carbons that we can convert into fuels. Although there are ways, if you can convert CO2, and chemically we're talking about reducing CO2, so reducing the number of oxygens or reducing the positive charge. So even taking CO2 to CO, carbon monoxide, is a big step in making fuels. Because once you make CO, you can use that with hydrogen by known methods and efficient methods to make gasoline. So any sort of this chemical reduction of CO2 is useful. But Bacarsley's very interesting work in that they're able now to take CO2 to produce larger alcohols. And it turns out that they do this with something called pyridine, which is a common organic chemical. It's like a benzene ring with one of the carbons replaced by a nitrogen. And this would be a hydrogen down here in pyridine. But it turns out that if you react CO2 with pyridine and different electrodes, in this case a gallium phosphide electrode, you can start creating these larger carbon. You can create alcohols and larger alcohols in this chemistry, depending on the combination of the electrode and the catalyst that you use. Sometimes substitutions of pyridine, where you put some different binding groups on there. So the mechanism of this is not very well understood at all, and that's going to be one of the challenges that we're looking at, is to try to understand how the electrodes and the catalysts play a role. One of the most important steps in this, the first step in getting this to go, is binding of CO2 to this nitrogen in pyridinium. So you get this CO2 bound to this. That's postulated in their mechanism. No one's ever identified this or seen it in real time, so I put that as a challenge to other people in my program to see if they could identify this, see if this is a stable species, or can we provide tools for the electrochemist to know how to detect this. So Mark Johnson at Yale University was one of the people to take up the challenge, and these turn out to be quite complex experiments to try to make these type of species, put them then in the gas phase, cool them, and then take infrared spectra of these cooled species. It's kind of an experimental tour de force, but Mark was able to do this using some electrospray methods to put these gently into the gas phase, into a vacuum system, and using some advances in cryogenic ion chemistry to quench these intermediate species and take very high resolution infrared spectra. And in fact, we're able to see this new band arise due to this carbon-nitrogen bond that was formed by CO2 bonding to this pyridinium ion. So for the first time, they've been able to identify that this is a stable species, give the people doing electrochemistry important information on the mechanism, and then giving them a tool now, a spectroscopic signature that they can use to probe this in real time in their electrochemical experiments. Another example of some probing of these intermediates in CO2 reduction is some work done at the University of Illinois. Again, some of the experimental work, the synthetic work, was done by Rich Maisel. And again, as I mentioned, if we can just go from CO2 to CO, that would be an important step. We can make what's called syngas there and produce fuels. But as you can see, there's a very high barrier to doing that. In electrochemical terms, that's called an overpotential. That's wasted energy that you have to put in to make that happen. It would be nice to try to reduce that barrier. And again, a catalyst is what we can use to reduce that barrier. So again, this species of CO2 minus is a key here. That's this key intermediate where we can get the CO2 to start reacting with things. And it turns out if we use an ionic liquid, which now has ionic species present, it can help stabilize this CO2 minus on an electrode surface, reducing this overpotential tremendously to make this now a possible mechanism. But again, this mechanism was very speculative. So Dana Delott in our program developed a very interesting compact spectrometer taking advantage of something called some frequency generation, which looks at molecules that don't have centers of symmetry or molecular systems in which there's no center of symmetry. So if you look at molecules in the gas phase, many of them are symmetric, but when they sit down on a surface, on an electrode in this case, it removes the symmetry, so this type of spectrometry is sensitive to species on the surface. So they're able to probe and watch this intermediate arise, this complex between the ionic liquid and the CO2 build up, and as well as seeing the CO products build up. So again, giving us nice insights into the mechanisms for these reactions for CO2 reduction, chemical reduction of CO2. Another thing that we'd like to do in making these alternate fuels, if you have that electrochemical process of reduction, you also need an oxidation process. And what's often done is trying to split water. Water splitting on titanium dioxide substrate is one of the typical examples, most commonly used examples of how that's done photochemically. That doesn't take advantage of the solar spectrum very well because TiO2 has a higher band gap, so it doesn't use a lot of red light. But one of our young investigators, Steve Cronin at the University of Southern California, found, though, that we can now take advantage of plasmonics that I mentioned earlier. If you put down gold nanoparticles, those have plasmon excitations in the visible. Putting down gold nanoparticles on the TiO2 substrate, you can excite this in the visible, create electron-hole pairs that start this chemistry going. And you saw an increase of factor of 66 in the oxidation of water on these TiO2 electrodes. And that's in kind of a crude system, very unoptimized. If you look at electrodynamic calculations of where the fields are in these type of systems, they're often at the junctions or gaps between metal particles, or here in this case at the gold TiO2 interface. So you have large fields over here that are driving this. This is, as I mentioned, then a very unoptimized system. If you can try to optimize this, take advantage of those fields, hopefully you can get much larger yields for the benefits of using plasmons to enhance this chemistry. So a couple of examples of trying to make fuels. We'd also like to now use the fuels and use catalysis to try to utilize these fuels better. These are some slides from folks at United Technologies Research Center, Med Colquitt and colleagues there, that just shows that as you go to a high-speed flight, there are a number of missions that we currently can't do that are limited by cooling. And here's John Schmischer was talking about chemistry, and now I'm talking about Mach numbers. So being neighbors is kind of rubbing off on us. But so some of these missions now are limited by the heat sink capability of the fuels. In addition, you could go to longer missions. Sometimes these fuels and catalysts clog up due to formation of carbon or coke. So we can either increase the speed of missions or the duration of missions. And so what happens, you have fuel flowing through the combustor, heat comes in, the fuel comes out heated up. If you just had some liquid go through there, it absorbs some heat. But you'd like to be able to absorb more heat. And so now we try to use what are called endothermic processes. So a chemical reaction that absorbs energy. It takes up energy for the reaction to take place. So it would act to cool, it would remove heat from the system as it's coming in. So we've had some endothermic fuels, but they tend to clog up. They've put catalysts on the walls to catalyze some of these reactions. And over time, coke or carbon starts forming up. It starts clogging up these systems. Then it gets plugged up, and then you kind of lose that part of the fuel system. So you'd like to avoid coke deposition to increase the limit. If you could then induce other chemistry, other endothermic chemistry to crack the hydrocarbons in there, you could get additional heat sink to enable future missions. So the endothermic fuels have been around for a while, but there have been some limitations, and I think some of the new understanding of catalysis is going to help us try to explore new opportunities in kind of next generation endothermic fuels. So we've had a MURI in this area looking at these nanostructures for catalysis, nanostructures that you might be able to make soluble, put them in fuels so they don't have to be on the fuel lines. Ultimately, we don't want to use precious metals like platinum or gold in these systems, but these are often model systems for catalysis. In fact, this group already has produced catalyst using zirconia that UTRC is very interested in, already starting to transition. So this MURI group includes people at Yale doing the synthesis, Lisa Pfefferly, Gary Haller, some folks at Tufts I'll mention, people using facilities at Argonne, using X-ray scattering at Argonne, to show that in the course of these experiments, these catalysts don't sinter. One of the interesting things and kind of insidious things about catalysts is that you can put something in, the reaction takes place, the catalyst changes structure, it sinters, it changes morphology. Then when the reaction's done, it goes back to its original form. So you can't probe before or after, you really have to probe during the experiment. So we've been able to do that, something with some experiments at Argonne. But in these experiments, it's cyclohexane dehydrogenation. So that's cyclohexane, six-membered ring, losing hydrogen. So it's losing two hydrogens at a time, and that's one of these endothermic processes. So it absorbs heat in doing it, but the products are still something that you can burn in your combustor. So it's a nice model system for an endothermic fuel. And in these experiments, they've looked at dehydrogenation of cyclohexane using different platinum catalysts. These are platinum clusters that are 2.15 nanometers, supported on some multi-wall nanotubes, so supported on a carbon substrate, and then some smaller clusters that are 1.32 nanometers. And you can see there's very different reactivity. With the larger platinum nanoclusters, you see cyclohexane as the major product. So this has lost one molecule of H2 in the process and a little bit of benzene. But as you use the smaller platinum nanostructures, and smaller, not that much smaller, going from 2.15 nanometers to 1.32 nanometers, you get different reactivity. This product goes away, then benzene becomes the major product. You have more dehydrogenation. So as part of this team, Matt Newrock, who's a theoretical chemist and chemical engineer at University of Virginia, tried to understand what was going on there, try to model this. And so in order to do this, you have to use a number of different types of calculations, electronic structure calculations to get structures and energetics, as well as kinetic Monte Carlo simulations to understand the kinetic processes going on. And basically, what he found is summed up that in the smaller nanoparticles, there are more edges. You know, if you look back at these structures, in the smaller nanoparticles, almost every molecule is on a corner or an edge. In the larger nanoparticles, you have some larger areas that are planes. And those molecules in the middle of the planes are less reactive, and things bind to them less strongly. So what he found with the small nanoparticles, the lowest energy pathway is dehydrogenation. So the cyclohexane comes in, sticks to the small platinum nanoparticle, and the lowest energy pathway is dehydrogenation. So it keeps losing hydrogens before falling off. In the larger nanoparticles, the cyclohexane doesn't stick as strongly to the large planes on the platinum. So desorption becomes the lowest energy pathway. So here, the cyclohexane sticks, it reacts a little bit, and then desorbs. It pops off the surface. So here, it sticks longer, reacts longer. In the larger nanoparticle, it doesn't stick that long. It just desorbs. So we could see we can model these different types of processes just because, that are different due to slight changes in size in the nanoparticle. But what's interesting, it also shows that there are different binding energies dependent on the size of the nanoparticle. So we have size-dependent binding energies. And the reason that's very interesting is when people talk about catalysis, they often use this construct called a volcano plot. And that says that in order to have catalysis, you have to have something that binds to the catalyst. So if the bonding energy is small, you don't get much catalysis. But if you bind too strongly, then it never leaves the catalyst, and the catalyst gets poisoned, and those active sites are gone. So you need something that's not too weak, not too strong, something in the middle. And if you plot binding energies, you kind of get this peak, and you get this the tip of the volcano. That's where you can predict what are the most active catalysts. But now, if the binding energy depends on the size of these nanoparticles, you'll have size-dependent binding energy. So for platinum, we're going to have a whole separate dimension of this volcano plot. So now we're going to start to see three-dimensional volcano plots, maybe more realistic, and multi-dimensional plots. So I think that's an interesting thing that's coming out of these findings of these size-dependent binding energies and ways to be able to predict what sort of reactivity is going on. Well, other ways that we can control catalysis. We'd like to control catalysis. As part of this mirror, you see, again, for a cyclohexane dehydrogenation, in these iron oxide nanoparticles, you get different reactivity if the nanoparticles are octahedra versus cubes. And we can enhance that reactivity by putting in a gold atom. So you see much faster reactivity with octahedra versus cubes. So lots of different ways that we can control this reactivity. We also use these soluble nanoparticles, make them soluble, put them into fuels to enhance ignition in fuels. This is work that grew out of some STTRs, SBIR and STTRs, in trying to enhance the ignition of fuels. And in a non-catalytic system, you can see here there's a long ignition delay time, particularly at low temperatures. Adding a catalyst, we reduce the ignition delay time by a couple of orders of magnitude. And here, these nanoparticles, we didn't even add nanoparticles. They added a palladium-containing solution. Those nanoparticles formed in situ. Hai Wang of USC did a lot of modeling, extensive modeling, and basically what he found is that these nanoparticles that are formed act as multi-centered nanoscale igniters. So they perform some catalytic chemistry, it releases heat, and then you see this bend in the curve. That heat that's released from the catalytic process then ignites the gas phase chemistry that goes on. So we're trying to understand some of these mechanisms of how these catalysts work to get this jump started. And again, found that we'd like to be able to make this work at even lower temperatures, and the key again is this binding energy. If you can weaken this palladium-oxygen binding energy, you can make this go even faster. So we're looking at ways to do that with different supports, different ways to control the electron density. Another way that you can control this catalytic chemistry, interestingly, is with temperature. This is work using gold dimers as catalysts for methane. And it turns out that you can have the oxidation or very low temperature combustion of methane. At higher temperatures, at room temperature, if you put in methane and oxygen in the system, you just find that the methane reacts to form ethylene. But at low temperatures, oxygen sticks to this system, and the methane gets oxidized to formaldehyde. And what's happening is, at low temperatures, oxygen here can bind to this gold dimer. Electrons get donated from this gold dimer into antibonding orbitals in the oxygen, and it weakens this bond. So the oxygen bond gets broken, the oxygen can then migrate, and they react with each of those methyl radicals to form formaldehyde. Turns out if you put different metals in here, you can get different products. You can get alcohols also formed. So you can model this now as two kind of different catalytic cycles. A low temperature cycle where you have binding of oxygen and combustion of methane, a higher temperature cycle. But it's an interesting question now, how do we optimize kind of coupled catalytic cycles? That something that we'll be looking at in the next while. But this low temperature combustion of methane is also a very interesting observation. Last year we mentioned we can put graphene, a lot of graphene going around. We can put graphene in to nitromethane flames that enhance the combustion. So we've done some modeling to show the reactivity of graphene where oxidation takes place on the edges, on the periphery, or even at defects, which count as as edge sites where the oxidation can take place. You can see the whole thing oxidized, and finally you can put different reactive sites on those defects in methane, and Mitat will mention some of that. We're creating tools also for theoretical chemists to use to model some of these catalytic systems. The 2010 Nobel Prize in Chemistry went for palladium cross-coupled reactions where, again, can knit together carbon molecules. But theory really couldn't handle that. But Don Trular, in our program, who's also on that MURI with John Schmischer, has created new density functionals that can describe these as well. Okay, so I'll just close up by mentioning a couple of things about ionic liquids. We've developed some novel ionic liquids. As I mentioned, one of the things we're interested in is igniting them or making them hypergolic. If you drop an ionic liquid into an oxidizer, you want it to just burst into flame so you don't have to waste time igniting it. Turns out with just one simple substitution, here is a hydrogen in this position, here a methyl group, you get over a factor of 60 change in the amount of time that it takes for that to ignite. So it's a new design tool for these in ionic liquids. We're working with Yue Chu of the RV Directorate in these multi-mode ionic liquids, and also looking at the reactivity of these ionic liquids, again, with a number of folks in RV, Al Vigiano, looking at reaction rates, modeling, and one of our top PIs, Steve Leone, is also doing joint experiments with folks at RV on this. Finally, the last thing I'll mention is some catalysis, not using metals, but electrons. So Al Vigiano at RV has discovered a very novel process of mutual neutralization. So two ions coming together, that reaction being catalyzed by electrons. It's never been seen before, published in Phys Review letters, and again, it affects modeling of plasma-assisted combustion, reentry, and the like. So you can see Catalysis has an application to a lot of DoD systems. There are lots of other opportunities. Be happy to answer some questions and talk to you about that later. Thanks.